¿Me escuchan todos por ahí?
Sí, se escucha bien.
¿Confirmación de que se escucha bien el audio?
Los escuchamos bien.
Ok. Vale, ¿nos escuchan por allá en México? Ok. Buenos días a todos. Sean bienvenidos a la primera conferencia plenaria del día de hoy, en el marco del segundo día de la Reunión Nacional Académica de Física y Matemáticas, RNAFM. Les recordamos amablemente escanear el código QR. Esta conferencia tendrá una duración entre 45 y 60 minutos, seguida de una sesión de preguntas de 15 minutos, en las cuales podrán formular sus preguntas directamente en inglés o si lo prefieren en español, y aquí les pongo sobre su pregunta. Este día nos acompaña el doctor Klages, quien se desempeña como profesor de Matemáticas aplicadas en la Queen Mary University, London, del Laboratorio de Matemáticas de Londres. El doctor Klages obtuvo su grado en Física en la Universidad Técnica de Berlín, en Alemania, y completó su doctorado en 1995 en el Instituto de Física Teórica de la UNAM. Después anduvo 9 años haciendo sus postdoctorados en Maryland, Estados Unidos, en Budapest, en Bélgica, y fue postdoctorado distinguido en el Max Planck Institute de Sistemas Complejos en Alemania. En 2004, el doctor Klages comenzó su carrera docente en la Conferencia de London, donde actualmente ocupa el cargo de profesor de matemáticas. A lo largo de su carrera ha escrito 5 capítulos de libros, editado 2 libros, publicado más de 61 artículos. Se interesa en la aparición de estructuras fractales en procesos de transportes caóticos como la difusión, y más reciente ha comenzado a aplicar la teoría de procesos estocásticos para entender los patrones de búsqueda de alimentos en organismos biológicos. ¿Sí me escuchan?
Sí.
Su trabajo en física teórica y matemáticas aplicadas abarca desde los fundamentos matemáticos hasta las aplicaciones experimentales. Es un honor para mí presentar al doctor Klages, quien nos hablará del movimiento de organismos y si estos pueden ser modelados por una ecuación diferente. Please go ahead, Dr. Reiner. Welcome, and you can start.
Okay. So I will just continue. So my talk consists of
Let me double check, doctor.
yeah.
¿Pueden ver las diapositivas ahí?
Sí.
En el auditorio.
So I logged in on two devices, on my iPad and on my laptop. And the video should be via my laptop. So okay, now you see my video. Okay, we can also try to do it that way. This is now via my iPad. That works.
Dr. Reiner, the way one before was working. They can see you on the screen as it was before.
Yeah, but do you now have a video of me?
Yeah, I mean, they can see you before also.
Oh, they could see me before.
Yeah,
Can you
yeah.
still see me?
Yeah.
Okay. Okay, but now I have switched on. Okay. Yeah, I'm not sure which video you have. I have now. Sorry for the technical problems. I have now two videos, one on my laptop and one on my iPad. So you see me live somewhere. I see the audience.
Yeah.
Okay. I'm not sure which picture you have now. Okay, give me a moment. Okay, I'll go back. Okay. Okay, we continue that way. So my talk consists of two parts. So first I will give more general introduction because if I understand correctly, not all of you are experts on the topic I'm going to talk about. So I will give a brief introduction to movement patterns of biological organisms and stochastic modeling in terms of drawing and motion. Then in the part two, I will just give an outline of what you might call data-driven stochastic modeling. So meaning one analyzes the data with the goal to construct a stochastic model. And I will just give examples for modeling the movements of sea turtles, bumblebees, and biological cells. And in part three, I will come back to the theory part in terms of how to model the movements of organisms. So I will go into more detail of how to construct stochastic models, especially in what I would call Newtonian dynamics in a co-moving frame. So this will be again more theoretical. Okay, so first of all, what I show here are three movement patterns. This one here are the pairs of about 60 white blood cells that perform chemotaxis in an experiment. Chemotaxis means that there is a chemical gradient, a chemical field applied parallel to the y-axis. And here are the paths of some cells of how they move, and you can see that they move on average parallel to the gradient while they still diffuse in all directions. So the second example is bumblebee flights. So we have here a cube, and here you see a carpet of artificial flowers where a bumblebee can get nectar. And this is a path of a bumblebee as it flies around getting nectar at these artificial food sources. So this is a laboratory experiment. And the third example is here. So this is the path of swimming in front of the coast of West Africa. So this is Dakar, the Senegal here. And in the ocean, searching for food. First of all, from a scientific point of view, you might be interested just to characterize these different types of motion. So meaning in all three cases, we see kind of random looking trajectories. And you might just be interested as a scientist to understand what's going on here, how these organisms swim, and to build mathematical models. if you're more looking at these problems from a practical point of view, then you could ask questions as following. Namely, first of all, it's important to assess cell migration patterns like that in order to classify cells. For example, you may have healthy cells, you may have deficient cells, meaning cells that are kind of damaged or they have a disease. And you may expect that these cells perform different types of migration. And if you can classify migration patterns like that, then you would expect that you can distinguish between healthy and deficient cells and therefore check for diseases in humans, for example. So it's important to understand cell migration, especially for checking for diseases in humans. This environment here with flower, and in fact, I will show you that I can put feathers with these flowers. But it is a bit on the leaves, and therefore here this one I can with the environment. And that's function of power balance always interacts with the environment. And the third case, for the actually not on the species. You know, we have to learn a little bit of how they're forming, how they're different. In fact, the path that we have years, and I really also study something like climate change, how they're looking at the point of awareness and what's the relationship. So provide integrated understanding for the things like that. Okay, so now how do you analyze this? Then we find out, like, we find a cell center. The cell center is different types. And the other is get the cover with cells. So this is the first stage of the data analysis. And then, of course, we want to realize further the data to make the cell of the data. So that means the cell technology will construct drugs according to the data and those quantities extract from the data in order to build the model. For example, you might be very interested in mathematics, of positions, of velocities. You might be interested in something like numerical display data, characterizes of how the cell moves after a certain time. And this information you can then try to build right in the cell. Once you explore it, then you can ask again about the mathematical, physical, and biological properties of these models. And you can try to interpret the model according to about how the cell or how the performs or how it moves. And how to understand the interaction of the environment based on the model that you construct. And once you have move on to the third stage, namely the data is one example. And I should say here, this is an example of the practical boundary here constructed from and this is an example of the search problem that can start on the computer. So the idea is to look at this list, random the play, and here we have many parts of this destination concept process, and it's just like meaning if you have input dynamics, the third dynamic is optimal in targets, meaning a certain setting. And now you can see this makes sense. Meaning that you minimize the time to come. The density of the dynamics are very so this is what you can study on the computer once you have set up the model, and then you can ask is this dynamics for some reason optimized have 16 optimized methods of evolution to find targets. And you might suspect that a certain organism has evolutionary optimized its strategy to search for food for survival. And then, of course, you can exploit this strategy for your own targets. Famous flight hypothesis, meaning it is hypothesized that animals have developed a certain in terms of daily forms of life to find targets, and this became very complex. This is one example illustrates this kind of issue. Okay. Now, in this talk, I will only focus on stages 1 and 2. I will not elaborate on the application of that search. This okay, now I will just illustrate some very basic types of methods, which then in turn may apply in order to understand the semantic data of foraging living. And the simplest we can start with are first random walks. And the need for recently, I saw that Klages was the first one. Some weeks ago, I was directed by my scientific from the University of Manchester, who told me that actually was third was in 1904. Actually, he was the first one to propose a simple random walk in the plane. Later, he did first like this. He explained the audience of the middle class he didn't see very discovered that the stimulus transfer malaria. So that's what the academics for. Therefore, it was very interesting in malaria and mosquito flies, and especially in the spreading of mosquitoes, because that's the way of how malaria is transmitted. So following, so we have an mosquito, and mosquito chooses where the flies are subsistence. And then I think the break leads or whatever that groups and then began to gradually and but he was not able to further the study this problem. Naturally, he expanded, and the one year after that was Klages, who already had much reputation this time in very biologically inspired mathematical models. So he wrote a letter asking for help on the problem of the mosquito spread. Well, Klages first replied, well, this is important, but at the moment I'm very busy. But 7 months later, this one is problem of the bit of progress. Well, I thought about it for more than a day. There's a capabilities, but this communication is going to be quite complicated. But we don't know if we can see the people better to actually people who is more skilled than myself and following this problem. And that's what Klages did. Then we explore this first letter in the problem of random walking. And this letter is on the following statement. Let's say here, a man starts from a point in open and was straight down in the straight line. Then turns into an alien, whenever it was another alien, the same direction. Now, if you think that we can talk about Ross, exactly the question that Ross posed to Chris, the amount of people who have done pieces replaced by working from a point, because this is more attractive inspired by the problem. And interestingly, you also see the reference for what was done. So now let's talk his own and he forgot about giving Americans sexual growth. Of course, what's very helpful about it. That's and so this letter like this was published in Nature. We asked for help, and so he was wrong. expresses the process meaning of the so therefore this is a one process. So it's not quite finished because actually 1 year later the biological series she was himself later on. You can see consensus from this data appears to this the family the species where do we say that supposed to the species itself the form and all so we have now the building and work proposed to model spreading of biological organisms. But in the way, of course, we are going to address first, that's what we are address because we are just close the roots when you ask the model the spreading of the species. Suppose was taken up by the Pearson and became a friend because once we have published everything about it, the Pearsons and then the use simple things in the to understand the movements of organisms. And you see what one of these so this was a first stage, and of course it's not more than one could do. Maybe around the same time, Einstein published one of his three famous papers in 1905. This one so Einstein published one other two on quantum mechanics and relativity. One for the quantum mechanics of mathematics and the other for the they indicated the first one to get built that indicated the displayed by in different methods for molecules. He did a theory on that, and this was published in this mathematical paper. The microscopic explanation of organisms in terms of the molecular distribution. And what you see here is from this pattern, within this later experiment, verifying Einstein's atomistic theory of organisms by calculating a large constant formless complex. He was a wonderful class. So you see this line now what is called and in fact, more popular and Einstein's original theory, we can have, say, super molecule, we can see here. So you see something this later. Now, proposed the model is quite by this simple differential equation. And this may be called this law of physics for the simple reason that if you forget about this term, we simply have to do the second law that force is equal to mass times acceleration. Mass times acceleration. Now, last previous idea was to simply model the velocity of the present particle theory by splitting the force from the right side into the second law, namely the friction temperature. So this is specific, meaning a constant times velocity, by which the particle that the particle loses energy. So if the present particle moves through the fluid, then of course it loses energy because it takes however, this is not the whole story, because only then it doesn't exist slow down and become to rest. Of course, the particle is also driven by molecules that is running molecules that you see also particle in water that is actually then the interaction between water molecules is actually driven by solid water. And this is modeled by function by points. So this means if you put function by points into a grade, the positive transfer grade, and then when you model positive transfer by types of forces, concentration, and then by the surrounding. That was what was here, and you have it down paper, by which formulated the famous manipulation that we assist. Now, another point of view, mind is something else. Then again, about process, because all this is very, very no correlation to get one of them. And indeed, mathematics correlates to the small but is not that will process for the university. So, of course, you can also use this model of an emotion to model biological movements in a more sophisticated way. But there's a certain type of stochastic process that is kind of unique. Namely, if you go to large fiction, meaning if you consider the so-called open-end large one equation, then you have a simple stochastic representation like that, that velocity or position or the time relative of the position is equal to noise. Where a point is going, that means you have come to white noise. Actually, well known to mathematicians as the Markov process, which again to the is not. So again, you see now we have a whole hierarchy of simple stochastic processes by which we can model diffusion. Then we frameworks, linear processes, or that are for physicists, or here the original equation, which is standard dynamics. So physicists actually call this one Brownian motion. So the other than phase, while mathematicians call the overlapped phase the process Brownian motion. So you see there are different terms in different communities. So you have to be very, very careful to talk about them both. Defining what you mean depending on the different communities. And all these different sorts of processes have been applied since about 100 years for modeling the movements of biological organisms. See, for example, this paper here from the 50s, where this was summarized instead of the articles. Now, however, there's a problem. As I've just argued on the previous slide, the Nacional equation was originally designed to just model the most of how electrons is moving in the field. But of course, this laser part was just passively driven by the surrounding water molecules. It does not move effectively by itself. It's not a organism. It's not a living cell or a fungi or whatever. But that means if you now want to apply the Nacional equation to biological organisms, you have a problem. So in a way, you are conceptual problem, then that's you apply equations that were designed to model physical problem to biology. Meaning we have to kind of modify this dynamics by taking into account that the active particle can take up energy from the environment and convert it into kinetic energy to by itself. And this now has been done, especially over the past in the field of so-called active particles. Where here I will especially elaborate on what is known as active Brownian particles. So there's a big field of so-called active matter, which describes phenomena like say, the clocking or birds, or the movements of cells of how they move collectively. And for this, you also have to understand how a single organism moves. And here we present now three generic models by which one can model in terms of dynamics of how a particle moves technically in terms of Boyle dynamics. We will see that all are formulated in terms of generalized non-quantum. Let's look at the first one. So here we have the underlying equation. We have set the mass of the particle. So we have acceleration on the left-hand side. And now you see on the right-hand side, I've generalized by making velocity or speed dependent. So here we have a friction coefficient that is not sloped, depends on the speed. And that way you can exactly model the take-up of energy from the environment and the conversion to kinetic energy, depending on the value of the speed. This is based on a given constant speed naught. So electric particle tries to stabilize at the naught. That's what it use. where this is obviously non-linear friction coefficient, so nonlinear dynamics comes into play. Obviously, I did the first performance, Schweizer, but that's starting from the 90s. But it seems that nowadays there are largely forgotten for some. But they were first talking about active quantum particles more than that. Now, the second model that became more popular particle lengths in terms of this non-quantum gravity. Now you see we are talking about an overdamped non-quantum dynamics. So just of zero. And now we have the first Gaussian by term that is before all actually environment passive directly. But more important, we have a predictive term, namely this kind of local drift term, meaning an active particle is supposed to move with a constant speed, not. But more importantly, you see here angle beta here in polar coordinates. And this angle beta in turn is driven by a Wiener process. So beta is obtained, or the derivative of beta, the time to is given by Gaussian by so that means one consultation with you. So many people actually call this model active quantum particle model, and this term because you see also the first one is obviously like one bandwidth. Also called this active quantum particle. So people that those define active quantum dynamics. But there's actually a third one, namely dynamics. Here you can sample the random variable actually from coordinated Gaussian noise. And for example, you can choose exponentially correlated Gaussian noise, this one. And this has been done by authors about 10 years ago. And so this is a first type of active quantum particle where the activity is due to correlations. And again, you see it's within the framework of dynamics. So I will argue that all three models should be called active quantum particles. When the activity comes into play, then a different way for each of these two models. So here, the most significant. Here, the potential of data and here the correlations. In terms of non-quantum dynamics, but you can also write down other stochastic models that are intermittent in the topic values. So this should be one of the ones different class of especially this combination is arbitrary So this is trying to work with the speakers trying to do his PhD on that, and the experiments were done. Is up here. And Peter is PhD by and Torres was a PhD student of this other. So now what I'm going to see the picture here of the figure actually with the sensor. So this is a so these guys can be very hidden and can be very long. So you see the length is 6 meters. The weight is about 120 kilos. And they can actually do this speed is up to a maximum of 25 kilometers per hour, which is quite amazing. Extremely very only a speed around 5 to 10 at most 20 kilometers per hour, which is still a lot. And recent times they have had about 20 tournaments since 2011, and then I followed the class by satellite tracking. These circles nested the Colorado and in the following, I will focus on the results for one and just detail for this step to 1,250 data points over a period of 400 days, so that more than 1 year in 2012. And here is the path of the sea turtle again, and you see it of how it swims. And there are 3 important observations just by looking at this picture. You can see, I'll try to make it for a little bit, that there are regular time intervals. So you see that actually it gets between the data points. So this is a big problem if you train animals in the wild. Meaning, depending on the quality of your sensor and where the satellite is, you may not get data with a constant time interval. You get position data points with a regular time interval. And this causes problems for any statistical data analysis because you want to expect statistical quantities like probability distributions of relation functions, which I will do in the following. This needs to be based on sort of constant time intervals. So again, this is taken into account for the analysis. Secondly, if you look at this chart, you can see that the turtle swims in terms of spatial, temporal, and latency. What do I mean with that? I mean the turtle does not swim on average with a constant speed. Look at here, where the speed variable labels the speed of the turtle, meaning whether it has a very weak speed or a high speed. In fact, you see that the turtle swims with around a good speed. But you see that there are periods where it swims with low speed, the starting points, and then stretches where it swims with larger speed. And you see that this is not homogeneous, but you can identify stretches where it swims with lower or with larger speed, and this is kind of called intermittency. So meaning that you have different phases of lower and larger, smaller and larger speed, which alternate. So this is a sign of limited motion. You see that this also depends on where the turtle is. So you have spatial, temporal, and intermittency. And third, so meaning kind of random circles by which the turtle swims. So this is exactly most when I first looked at this chart, that there is this random looping that of course if you have some explanation, and it's quite different from a single chromatic process. So if you look at this, you may ask yourself, okay, now if you want to construct a stochastic model for that, would you see that this document looks like a passive Brownian particle, like ordinary mathematics? Make up your mind of whether you would guess that such a model would apply. I'm going to discuss that in a moment now. But hopefully, this kind of looping may cast out that this is simple and Brownian dynamics. But now, the data analysis, the first thing we need to look at is by extracting the speed of the turtle. And here you look at the probability of the turtle speeds. And here you see that the turtle swims at rather small, up to 2.5 kilometers per hour. And you see that this actually matches quite well to what is known as a radial distribution, which is a two-dimensional Boltzmann distribution. So you see it goes to 0, it's equal to 0. And then it decays exponentially. So it's like v times v to the minus x squared. And here we have a so-called contact plot. I'm not explaining what the contact plot is. But in a way, if you see that in this plot, that the data, which is here the blue line, matches to the dashed red line, which is the radial distribution, which is here just linear. Then it seems that there's a reasonably good match, and this holds especially for small speeds, while for larger speeds there's a deviation. But here again, you see the Reunión plot, and this is a plot. The Reunión plot, you can of course check for exponential tails and not for polynomial tails, and this doesn't correspond to contact plots. But I mean, here you don't see a big deviation between exponential tail and indeed you can see that the exponential tail is a bit better. So to prove this, that actually the turtle swims the speeds, the speed according to the rate distribution for smaller speeds, while for larger speeds we have the exponential tail, so e to the minus speed. And we have to check that for other turtles as well, so that seems to be a general feature of the turtles that we check. That's what I've written down here. And indeed, that we have the radiator small speeds and exponential for larger speeds. Exactly related to the spatial intermittency that I have shown you before by just looking at the cards. So we see both. And I may remark that the same pattern applies to the velocity distribution. So meaning you can expect the velocity distribution parallel to the x-axis or parallel on the y-axis. And then again, we find that in the center diagonal where it details the details here. Now let's look at the second main unit for constructing a stochastic line calculator, namely the velocity of the correlation function. Statisticians call this autoprogram. So here is we have because they're also different. So each is an individual, so you cannot therefore, only we can do expect the correlation function and the distributions time parameters. And therefore, we need to define the velocity of the correlation function, meaning a velocity along x here as an example at this time I times x times time I plus n. And then you look at the discrete time multiplied by the time curve. So what you see here plotted on the x-axis is the hours. And on the y, this is the correlation function on x, and here the correlation function for the velocity on y. And now you see the following. First of all, well, it's not so easy to see now, but indeed you can check that for very short lines, we have nice exponential here. But now you see that for longer times, you have persistent oscillation. So actually, this kind of line, this is the exponential data. If you see that indeed the turtle oscillates persistently over certain periods, so here it becomes a little bit more random, but then you see it becomes persistent again. So this is along x, y along y. You see there's also a pattern like that, but it's more so this is something that the turtle does by itself. You might find evidence slides later. But this is certainly not simple Brownian motion, it's something else. It's a non-Markov process in any case. So in that sense, this is the correlation today, is what I call Brownian effect. Okay, so now we know so now that this we can see then takes not equal to noise. Where noise is exactly the Gaussian distributions for this velocity along x and y. Gaussian in the center with exponential tails, and correlated according to the correlation function that you see below. So this is our stochastic model constructed from data, and now that as you can see here, the term only swims in a specific region. So you see it's kind of bound in this direction, where this bound is tricky because it's a close line, but it also seems to be because not so far away from the coast. So there's a bound here you see where for some reason the turtle prefers not to swim any farther. And so we model these boundaries by putting this dynamics into asymmetric harmonic potential. So harmonic potential, where the key factor is steeper here than here. And now, if you put this smaller, you can connect this like that. And this is a bit messy, but it's qualitative. You see again that you have groups you need to check that in much more detail. So, for example, displacement x squared, meaning the mean position where you can find the turtle at time t. And what you can see here in the double logarithmic plot, the following. So the blue line here is the integral displacement extracted from the experimental data. And you can indeed see that the term for swims super diffusively. That means it swims according to a power law with an exponent b that is larger than 1. So for the need to be swims faster than y. It's b larger than 1, which we find b equal to 1.68. And indeed, this is characterized when used by a simulation, when we get 1.55, which is not too bad. Indeed, this is the red line, which here because it overlaps with the experimental data. And the green points are results for different realizations of the randomness in the simulation. So you get different time averages, and you see that they are very aligned with the average obtained from the data. And you also see that for longer times, actually, the turbulence goes down. So you get substitution. Actually, eventually, this will localize for the simple fact that the turbulence does not swim any farther along the x direction because of the boundedness. So this is reflected in these results. Note also the spreading here of the spread results. So if what is going on, the first one is called microrealistic rating, but here I don't go into detail, so this becomes here quite a functional stochastic process. Okay, so we have quite a nice matching for the investigation to our simulation, of course, the correlations and the from our experiment. But there's more to say. Maybe now let's elaborate a bit on the interaction of the turbulence environment. You might suspect that the turbulence is perfectly driven by the ocean currents. And indeed, it was argued that way by other scientists here in this field who also analyzed various sea turtles and turtles, but I think small species. And here, the birds are just driven by the but you can't get that all of those. So there's actually a excellent data available. And you can do it on the computer, in a person, and then you just, this one is going to you see that the parts of the spaces are totally different compared to the parts of the journal group. So this is the journal pass, and this is the present pass. So therefore, all terms definitely do not just tested driven by the ocean currents. And there's another aspect. Here you see the chlorophyll concentration in front of the coastline, and the chlorophyll is in terms of concentration. And you can see that indeed the terms align themselves a little bit with the concentration gradient, assuming the gradient, you can also see it here. This is the environment that we have not built into our model. We find our model we have to take this coupling with the environment into account. So this has nothing to do. Now, let's get a little bit and suspect so you might check whether actually the loops are from one point to the next one. to see the correlation between them. Not quite mentioned the 20 kilometers, but at least it's not far away. Given all the assumptions that we've done here, for example, it's hard to exactly find Frege region here. I would say there's something about it, meaning that are that large that the distance with these targets. Five minutes. Yeah, that's fine. But 5 minutes is not much. So that's slow. I have to speed up. Okay, second is cell chemotaxis. So let's look at cells performing chemotaxis. So we have Gaussian noise, which is related as a power law. And we have so it's kind of different by a power law detail. The cells perform super diffusion. And so I don't go into detail here because I'm just getting started. But again, you can construct a different model like that because the power law with power correlated Gaussian noise. And it matches well to the data that we obtain from experiments. Let me move on to the body piece. So this is our body experiment. So again, we do one body into this cage. It's 4 liters per hectare. Then we can extract again velocity distribution. This is the development of velocity distribution, meaning the top line. And we can take in the last protein here and the last protein here. So these are the velocities very well. And now what we can do is we can use flowers, meaning the bumblebees are trained to avoid flowers with spider image on them, and so therefore protect spiders that nature catch bumblebees and them. And the bumblebees are trained then to avoid flowers with spider image on them. And there are 3 phases without going into with spider images. One day later. Now, what you check is whether there's any change in the speed and the velocity distribution so that means whether or not the bumblebees are threatened by spiders, they move with the same speed. But the velocity that changes. So all the cognitive environment is in the velocity correlation. Namely, the red velocity correlation is without spiders. So you see that here, the bumblebees fly persistently, so that moves steadily towards the ground without interference. While they move anti-consistently, meaning they move to a flower but make turns, by which the correlation becomes negative. So they are more careful in their turn to avoid the flower's spider energy. So they adapt to the environmental threat by not modifying the speed of the velocity, but by modifying the correlation between. And again, in the model is over than comes one by putting in this velocity and the correlation. Now, this is the data. Also, I have some time left to say something about the stochastic modeling. Namely, now, in terms of stochastic model, you mentioned as yourself, how do you, as a human, how do you move? How do you make a step? How do you make a single step? Well, it is I make a step by choosing a certain angle and by choosing certain step lengths. And then I repeat the process. And I may need persist. I certainly do not calculate my step in a Cartesian frame. I calculate the x component of the step, I calculate the y component of the step, and then by adding both. At least I don't do that. And I choose a remainder and I make a step. Right? But that was exactly Pearson's and Ross' formulation of random walk. Namely, that this is of how a human or animals move. And this means moving in a two-moving frame. So if you calculate your turning angle, this is what I would call a two-moving Cartesian frame for making your step. And indeed, that was already realized by movement ecology, a discipline which studies the movements of organisms by in terms of what's called a correlated random walk. So what is a correlated random walk? It's exactly the following. So you move in a two-moving frame choosing the speed, and for this type of model, the speed meaning you make a step with a constant step length with turning angle that is randomly chosen identically from a non-uniform turning angle distribution. Non-uniform symbolic persistence because organisms may prefer make a step in a certain way. This is called the correlated random walk with model persistence. But it's interesting observation. This is identical to the active random motion of particle type 2. Because if you transform this correlated random walk back to well, I mean, you get back to simple particle type 2 model that I introduced before. This formulation, the speed times the concept and the sign of orientation. Most identical, which event is very actually noticed by the communities of movement ecology and active movement. And another interesting observation is that in the moving frame, the that the same process is not enough. But this is very known. Maybe you have stochastic differential equation for the turning angle. This is the acceleration of the turning angle, and you have noise, which can be arbitrarily distributed and arbitrarily correlated. Same thing for the speed, you have the acceleration, you have the noise. So this is my proposal of how to roll, for instance, movement in a moving frame. And now I would argue that this modeling combines all three different types of components. Certainly, if the difference the speed dependent, you will become active on most type one. If you have not uniform angular noise for this guy, you will cover active on most type 2. If your noise is correlated, most cases, well, you will cover active on most type 3. So by using this framework, you have every different types of without going into further detail. And as an example, we should construct such a model from data. So we found that for boundaries, and without going into much detail, I think that's on the paper from 2030, what we obtain is the following. So for the turning angle, we find a simple equation like that, again, constructed from data, meaning here the angular noise is a direct Gaussian noise, and it's correlated according to a polar indicator. So in that sense, here we find that our probability is according to active and most type 2 and 3. Because noise is correlated and it's not uniform. For the speed, we obtain this equation from data. So you see we have a speed dependent friction coefficient. Actually, this is called radial friction. So we have motion type 1, and the noise is actually which is anticorrelated. So we have also equicorrelated. So here we have an example of generalized Gaussian dynamics in the moving frame, modeling memory flights containing all three features of the equicorrelation. So this is what you can do by this combination. And just to wrap up, I still have about 2 minutes to elaborate that I'm doing together with Física, sharing. So this is motivated by a recent experiment. It's Alexei Titi, who's also a student of Klages. So they made an experiment where they drive the fields. And they can drive the particles so that it exceeds the whole spectrum of noise diffusion. They need to know how to set the step length and the turning angle for this particle in the dynamic frame with the velocity relations. So therefore there is belief to define living blocks, the friction motion in the dynamic frame so that we can implement the parameters. Living blocks is easy, actually, namely you simply set your turning angle and you set your step length for a linear distribution meaning for the characteristics. But indeed, this defines only one type of 3 different types of Lagrange. This is listed by here some years ago. Namely, you can actually define 3 different modes of Lagrange. Two are defined in the Cartesian frame, one is defined in the Newtonian frame, and all 3 are different. If you want to check, you find details in the data, but that means you cannot transform all these 2 different Lagrange models defined in Cartesian frame into each other. So it depends on the frame, the use of what analysis you get. And for friction random motion, the test was really very helpful. There's very lot of how to define friction random motion. This will turn it on. And now the final slide is now as an example of what we're going to try to do. At least the simple two-dimensional concept process. The way to do it is as follows. So in terms of S and the manipulation of the vertical theta, then in fact you see we now have to start on this problem because both S and theta are stochastic variables. So here by applying the Ito equations, this is what we have for the where these are both by dimensions. Now we look at the dynamics of the compute the turning and distribute on this right hand side. What is obtained is this one for the turning angle, this for the interesting. So we see that the turning angle is distributed but now here's the model. So how was a solution for the transform for we are alpha is represented by this speed is distributed solutions exponential coordinate gradient. Now I'm done. So this is the summary. So what I'm proposing here in this work is and I will put you on the subject is the licenses to the right. And here I propose just to do the same for the participants. And this proposal based on both and for stochastic modeling. And so, yeah, this motivates to develop a stochastic theory for two-dimensional processes in the programming field. And finally, I want to give credit to Luis, so here there's a list of different people contributing to different topics on sea turtles, circular Texas properties. Thank you, Doctor, for the interesting talk. So it's time for es hora de sus preguntas y veremos si nos podemos traducir al inglés. ¿Alguna pregunta? Sí, claro.
Yo quiero preguntar por el caso de los caminos realizados por las tortugas o los datos tomados de esos, ¿se considera a las tortugas camino individual o también se toman en cuenta las interacciones con las demás tortugas?
Okay. They are asking if when you analyze the data of the turtles, do you consider interaction with other turtles or do you consider the turtle moving by himself? So all the turtles move individually. There are really swimming those that cover very large distances. So you've seen several hundreds of kilometers. So to my knowledge, there are no interactions with other turtles that swimming alone. Certainly, they're also nesting on islands. But this is not something we have considered here this morning. No, this is just about individual turtle movements. And in fact, this also applies for the chemotaxis. We have different cells on the same substrate, but again, approximately they are moving at the same volumes. Collective dynamics would be something very different. Ok, para el análisis en este caso, se ha considerado que las tortugas se mueven solas, no se considera la interacción como movimiento en grupo con otras tortugas, aunque cuando llegan a las islas y ponen sus huevos, podría ser un caso diferente, y el movimiento colectivo no se ha considerado en estos experimentos y sería obviamente un poco más difícil. Okay. ¿Alguna otra pregunta por ahí? A ver, Luis.
Well, thank you very much, Roberto. First of all, Professor, thank you very much for your talk. It was really thought-provoking. I enjoyed it a lot. I would like to ask related to the talk on the correlation equation that was derived for the example. In that particular case, it was mentioned, I think, that you required particularly intervals of time to be at a specific environment. And also in a previous slide, it was also discussed that not all the data was there, pretty much. That when they were up in between the data taken, how did you recall that problematic?
Excellent question. Thank you for this. So, this is yeah. I'm going to translate this to Spanish or yeah, okay, that's fine. Yeah. Okay, Luis preguntó que si cuando encontraron la autocorrelación de las velocidades para las tortugas, había mencionado un problema en que había fases en las que el intervalo de tiempo era diferente. Entonces preguntan que cómo hicieron para encontrar autocorrelación correctamente, debido a que hay una interpolación. Yeah, again, as I said before, as you see here, there are gaps in the data, and that means the time intervals are distributed irregularly, while for the data analysis, we need a constant time interval. Otherwise, you cannot reliably construct any probability solution, and the same, of course, for the correlation function. So what we did was, certainly you can do more sophisticated interpolation, nonlinear, and so on, but that may cause other trouble. So you just interpolated linearly between the data, and then we sampled the data with a constant time interval, which was the average time that we had here in the data. And that was the basis for computing the probability distributions and the correlation functions. You might want to translate it.
So, básicamente dice que cuando hay espacios vacíos en la información que ellos recaban experimentalmente, hicieron la interpolación lineal para poder asumir que existe data ahí, pero que se pueden hacer estudios más sofisticados para poder encontrar la verdadera posición de la tortuga, aunque en este caso se consideró una interpolación. Y ahí se calculó autocorrelaciones.
Okay, that's what I mean. I mean, this is a crucial point because I learned that you have to be very careful here. And you have to very carefully check the dependence on, say, the time interval that you choose and anything else. For example, if you choose a very large, a very small time interval, then the oversample, then you get very distributions. So if you're not careful, you can get anything you want from it. So you have to be very careful that you but this is something that we're trying to do.
Ok, dice que hay que tener cuidado porque este es un punto crucial en el tamaño ahora sí que del intervalo de tiempo en el que se calculan las intercorrelaciones, porque si se elige apropiado, como es data experimental, uno puede obtener muchos valores. Y la regla de esto es trabajo en progreso para después, usando otro tipo de ajustes. Luis.
This is the first thing I remember.
¿Alguna otra pregunta? ¿Está por ahí el doctor Lee?
Se tuvo que retirar, doctor, pero ya no hay preguntas. Ya no hay preguntas aquí en el auditorio.
Ok, por lo del diploma, eso
se le hará llegar posteriormente por correo electrónico.
Ok, perfecto.
Muchas gracias.
Okay, they say thank you to you, doctor, and they will send you a diploma for this.
Thank you very much. Thank you very much for the kind invitation. Again, it was really a pleasure and honor to speak. And thank you very much for this.
Dice que muchas gracias por su invitación y que ha sido un honor para él estar aquí. Okay, I think it's everything.
Muchas gracias, doctor. Hasta luego.
Thanks a lot again.